So let's do another problem with some oblique shocks. In this case, we have a wedge. Beautiful. I love it. And let's see here. It's got a 15-degree half angle. And just so you know, that half angle is actually equal to our deflection angle. Okay, so that is the deflection angle. It is going to be in a Mach 5 flow, and if it's in a Mach 5 flow, well, guess what? It's going to cause a shock wave. What? An oblique shock wave, hopefully. So what we're going to try to find this time is something different, okay? Something different. We're going to try to find out what the coefficient of drag is for this wedge. So what is the coefficient of drag for this wedge? Now, that drag coefficient is going to be based on the pressures. So I'm going to have a pressure here on the top. P2. I'm going to have that same exact pressure on the bottom because it's, it is symmetric. So I'll just call that P2. I could call that P3 if I wanted to. If it was an angle of attack, I could make it P3. And then finally, right here, on the back, I'm going to have pressure pushing it on that side too. I'm going to call that P1, okay? I'm going to call that P1. And just so we can do this, we're going to make an assumption. We're going to assume that P1 is equal to our free stream static pressure, okay? We're just going to assume that that'll make things a lot easier on me because then I can say, well, I already know what P1 is over here. I can do everything with that. What is P1? I don't actually need to know it, surprisingly enough, to solve this problem. It is completely irrelevant. Okay. So let's see here. How are we going to make this problem work for us? Well, first off, we don't have a span, so we'll have to make this per unit span. So instead of being a capital D, I'll need to make that a lowercase d because we're doing it per unit span. And that's going to have this equation. So that'll be coefficient of drag per unit span is going to be equal to my drag per unit span all over my dynamic pressure, 1, times the aspect ratio. That looks pretty good. Oh, aspect ratio, sorry. The surface area. There we go. And that works out fine for us. So what is that surface area? Well, it doesn't give us one, does it? No. So why make it hard on ourselves? Seriously, why make it hard? So what I'm going to say is that this area is going to be equal to my chord times 1. Okay? That's just going to make it a lot simpler on me. And this Q looks a bit crazy here. I'm going to draw that Q just a little bit nicer. There we go. That was a Q. That was meant to be a Q. Okay. Now we got to figure out what my drag is going to be in this case. Now remember, drag is always coming from that pressure. Okay, we have a pressure on an area. We're going to be using that to solve everything. Okay, we have this pressure on this area. And as a note, the C I'm talking about here is the chord, and that is going from here to here. I didn't put that in my diagram, or else I should have. That's my chord. There we go. That looks good to me. Yeah. Okay, so now let's figure out what drag prime is, because most of the other stuff is pretty easy. So that's going to be, if I'm looking at it from this way, my pressure is going to cause a force. That force is going to be perpendicular to the surface, right? So I can call that force 2. I can call that force 2 as well, right? Everybody okay with that? Make sure I got everything else doing good here. I think I do, yeah. And so that force is going to have 2 components. It's going to have a component that is, pushing up or down, which is going to cancel each other out. So it's going to have this vertical component. It's also going to have a horizontal component. And since this is perfectly symmetric, those vertical components and those horizontal components are going to be identical. Now, which of those components actually leads to drag? Well, it's the horizontal component. I also need to realize that on the back, I'm going to have a force as well, okay? And that one's pointing perfectly in the direction of trying to push it through the flow, but obviously that's going to be overcome by the pressure behind it. Okay, so we're getting there, but we still have to figure out a few more things. First off, or second off, or whatever, third off, I don't know where we are. Pressure is equal to force over area. Okay, and I can rearrange that to say that force is equal to pressure times area. But what is my area? Well, I'm going to introduce a new variable to help myself out here. That variable is going to be called L. I'm going to say that this length right here on that surface is called L. Okay? And so that force, like P2, I'll just do it, yeah, P2. Or I could say force 2 is going to be equal to P2 times L times 1 because it's a unit span, right? Okay. Now, I've introduced a new variable. I really don't want to keep a new variable for very long because I already have the chord here that's one variable. Let's see if we can get rid of this length. Well, luckily we can. I know from triangles that if this is 15 degrees, that is L and that is C. Can I solve for L in terms of C? I can. It's not that bad. So, cosine of 15 degrees is equal to C over L. I want to solve for L, and so what I get then is that L is equal to C divided by cosine of 15 degrees. So let's plug that in there. So force 2 is equal to P2 times C cosine of 15 degrees, and times 1, I'm just going to leave the 1 off. Okay, I'm getting closer here. This is not bad so far. I think we can keep on going, and we'll figure out what force 1 is in a minute. But now, I have to figure out what is the component of that force that is actually going in the horizontal direction. What is that component? Now, if you're not absolute wizards at trigonometry, that's okay. Become one. I'm kidding, messing with you. You're like, what? No, I'm kidding, fine. So let's do it. I'm going to do it by zooming in on this diagram right here. Let's see here. That looks good. Let's bring my force down. Perfect. Okay. Just to help myself, I always like to put the two tips of the triangles together. It just really makes it easier for me, and I can do that because I'm just drawing this diagram. So this right here is still force 2, and I'll say that this is, force drag 2, I guess. We can call it that way. So I need to figure out what that angle is. Well, luckily, I know that this is 90 degrees, right? Okay. And so that means that this angle has to be 75 degrees. I also know that this angle is 90 degrees, which means that this angle has to be 15 degrees. And ha-ha, I got an angle. I can do everything else from there. So, let's see here. Force drag 2, okay, so that's 15. That's opposite over hypotenuse. So sine of 15 degrees is going to be equal to force drag 2 over force 2. Okay, and so then force drag 2 is going to be equal to F2 sine of 15 degrees. That is starting to look pretty good. As note, I could leave it in terms of the angle theta if I wanted to, but we have the angle, so why not use it? So I'm going to plug in what I have right here into my equation. And so I get that force drag 2 is going to be equal to P2 times C times sine of 15 degrees over cosine of 15 degrees, which is simply equal to P2 times the chord tan of 15 degrees. Okay, so you can see how we're starting to make progress here, right? We have force drag 2 right there. Now we need to get force drag 1. Okay, so similar process here, but I have to figure out what this area is. Like, what is A1, okay? Question mark. So let's start walking through this and figure out what A1 is going to be. So I'll get all the values I know. So this right here is C, that's theta, this is the length, and I want to get a value for this right here. So I'm going to call this guy length 2. Well, I know that if I was doing it by triangles, half of length 2 is right there, and that's pretty easy to deal with, isn't it? Because that's just a right triangle. I have it. So let's do it that way. I can solve for length 2 this way, I believe. So I have opposite over hypotenuse, that is sine, right? Yeah, sine. So what I would get then is that sine of 15 degrees, I'm doing it because I have this guy. Wait a second. Ugh. I am a doofus, everybody. I apologize. I was doing it in terms of L. I don't care about L anymore. Okay. I have opposite over adjacent. That's tangent. Okay, there we go. Sorry. Your teacher makes mistakes. So I have tan of 15 degrees is equal to 1/2 L2 over C. And so I want to solve for L2. So I multiply both sides by 2 and C as well. I'll get that 2C tan of 15 is equal to L2. Okay, so that's helping me out. So I can go back to my pressure equation. As you know, I know pressure is equal to force over area, and therefore force 1 is equal to pressure times area. And A1 is simply going to be equal to the length 2 times 1, because if I'm looking at the back of this guy, that's what I'm seeing here. Okay, that's length 2, that is 1. This is a, more 3D drawing of that wedge. So that's going to be equal to P1 times 2C tan of 15 degrees. You can already hopefully see a pattern forming here, right? I've got tan of 15, I've got tan of 15. I've got C, I've got C. I've got 2 in one case, I've got 1 in the other. So now with this, let's go ahead and finish up drag prime. So remember from this diagram that I have a drag force acting on both, both locations. So there's one on the top, and there's also one on the bottom. So this is force drag 2, that is also force drag 2. And then finally I have, force 1. So I've got 2 force drag 2s, right? So D prime is going to be equal to 2 times force drag 2, which we have an equation for. That's P2 C tan of 15 degrees. That looks good. And then in the other direction, I have P1 C tan of 15 degrees. Okay. I like it. That looks good. Now let's plug that back into my initial equation. Because remember, we know that the coefficient of drag per unit span is equal to my drag prime over Q1 times C. So that's going to be equal to, and for simplicity's sake, that's a 2 there, sorry. I'm going to pull out the 2 tan and everything else. So that'll be 2C tan of 15 degrees times P2 minus P1 all over Q1 and C. The C's cancel, so my chord doesn't matter. Who would have guessed? All that we care about is angles. Nice. And we are getting so very close here. So very close to getting this problem done. But we're going to run into one more issue. I have a Mach number, 1. I know what that is. It's equal to 5. I don't know the temperature, I don't know the pressure, I don't know the density, I don't know any of that stuff beforehand. So usually when I do my dynamic pressure, Q1, it has the following equation. It's equal to 1/2 rho v squared. I can't find my velocity if I don't know my speed of sound. I can't find my density if I don't know something else. So I'm stuck, there's nothing we can do, the problem's a goner. Oh well, we tried. Or maybe it's not quite a goner yet. So we're going to have to use some definitions here to help us, okay? Goodness, definitions here to help us. So to do that, let's walk through this. First off, does anybody remember what the speed of sound is? Gamma RT, right? Okay, so A squared is equal to gamma RT. And if we look at our old equation, man, I'm talking country all of a sudden. We know that P is equal to rho RT, right? So let's solve for RT right there. So I get P over rho is equal to RT. And I think you might be able to see where I'm going here. I have density in here. Why not start plugging in the other things I know? So P over rho is equal to RT. I'll plug that in. So A squared is equal to gamma P over rho. Did I do a good job? I did a good job. Okay. So why don't we try to bring in a gamma P? If we can do that, we can actually get much closer to having this solved. So I'm going to do that. I'm going to say, okay, Q, you're equal to 1/2 density times gamma P over gamma P. And this is P1, just so you know, these are all P1s. Okay, and this guy right here, that is going to be equal to my speed of sound squared. Just inverse. It's going to be 1 over my speed of sound squared because it's upside down. It's not pressure over. I did a good job there. Where did I go wrong here? P over rho. Sorry. My handwriting is the thing that confused me. Okay. So I have this one, gamma P1 over gamma P1. There we go. So this guy, that's what it's supposed to be, is equal to my speed of sound squared. So I'm going to plug it in. So I get that Q is equal to 1/2 gamma P1 over A1 squared times V1 squared. Okay. Now, what do I call a velocity divided by the speed of sound? Mach number. That's my Mach number. So that means that this is simply equal to my Mach number squared. So Q is equal to 1/2 gamma P1 times my Mach number squared. Okay. Whew. Took a while. We're making it there, aren't we? We're making it there. So with this, we can then plug this back into our equation all the way back up here. And we're okay with this because we can find ratios. We don't know what the actual number is, but we can find the ratios from our tables. We can do that. So let's go ahead and do that. So CD is going to be equal to 2 tan of 15 degrees, P2 minus P1, all over 1/2 gamma P1 M1 squared. And if I want to, I can then make this a little bit prettier. So what I'm going to do is I'm going to bring the 1/2 and the 2 together. So that will be 4 tan of 15 degrees over m1 squared. And I'm going to divide p1 by both of these guys. So I'll have p2 over p1 minus p1 over p1, which is just 1. So if I can find out the ratio of p2 over p1, I can find my drag for this problem. And I can do that because this equation, everything I need is just this value right here, and that is going to come from Appendix B, because remember, all that long time ago when we started this problem, it was all dealing with an oblique shock wave. Whew, we have just been flying through this. There's a lot of stuff here, a lot of derivations, but it was important stuff to see how we can use our shock waves to get important information from a wedge. So let's do this. So we have m1 is equal to 5. We know what our deflection angle is. That's equal to 15 degrees. But what is beta? Okay, what is beta? We have to go to our theta beta Mach diagram for that. In this case, I'm just going to give you the value. It comes out to be 24.2 degrees. And then from that, I can go and get my normal Mach number. We can go to the tables and we can solve. So my normal Mach number is equal to my Mach number sine of beta. And if you're wondering about like just how this would look, that right there is the 15 degrees. This right here would be the 24.2 degrees, okay? Important information to know. As a note, this little angle right here, which is like about 9.2 degrees, gets smaller and smaller and smaller the higher your Mach number is, which is more and more dangerous because you have higher and higher temperatures right next to your surface. So this is m1 sine of beta, so that means that's 5 sine of 24.2, which is around about 2. It's actually equal to 2.05, but for the sake of my sanity, we're going to just say it's 2. And all we have to look up to solve this problem now is to go to Appendix B and say, what in the world is our P2 over P1 for that Mach number? So for Mn1 equals 2, what is P2 over P1? I'm going to tell you that it's around about 4.736. And with that, we have every bit of information we need to plug it in there and get what our coefficient of drag would be. And so using this equation, we would get that our coefficient of drag for this diamond wedge airfoil would be equal to 4 tan of 15 degrees over Mach number of 5 squared. Whoop, I left a gamma out here. Sorry, there's a gamma there. Times 1.4. Times my pressure ratio, which is 4.736 minus 1. And that would be equal to 0.114. And we would have it. And that would be it. We'll be done. Beautiful. Beautiful. We've got it. So there you are.